The variations on these. We talked about open die forging and closed die forging. If I start with a cast pancake or a great big bar and slice it off into pancake, a round bar, and slice it off into pancakes, I might forge it into what would be a turbine blank, or it might be a pump turbine or something. This one's cut in two, and if you look on the edge, it's been etched, and you can actually see the grain flow. Metals will develop sort of a woody texture to them depending on how they've been formed. I mean, the cast structure, I passed around that copper piece before, the continuous cast copper piece, and you can see the grain structure. But you want to actually break up that grain structure. In fact, that was the problem with that copper, the copper wire. The grain structure was too coarse, and it destroyed the properties. It made the surface bumpy, and when the train went down the track, the electrical contact, which is like 12,000 volts or something like that, would just go spark, spark, spark. It looked like the 4th of July as the carbon brush was sliding along this bumpy wire. Now, the wire didn't look bumpy. You had to measure it. There was only about 1 or 2 thousandths variation in the undulations, but it was due to the underlying structure of the metal. So forging will give you good, if you design your dies properly, can give you very good grain flow and structure, because the metal can tend to split just down the grains, just like a cord of wood would. Cord of wood would? Could. Cord of wood could. So far as that goes. Now, there are a number, anybody have any questions on any of that? Yeah.
So you cast something and then you actually forge it to consolidate?
The pores, to get rid. A forged product is usually considered a very high quality, also read high cost product. Okay. For example, if I was designing the landing gear on an aircraft, it's going to be forged because it's consolidated. I don't want to take the chance of the big flaws, very high strength steel. On an automobile, where the value of a pound saved is not as great, in the old days, they might have used forged steering knuckles and components on the wheels. Today, they use ductile iron castings. Okay, they can't use gray iron castings because it's too brittle, but ductile iron has about 15–20% elongation, depending on the grade, and the stresses are less. I mean, you don't go landing your car like you do a 747, right? So in that case, they can't afford forgings for cars. I mean, the difference in a forged steering knuckle and a cast steering knuckle might be worth $1, as you know, to General Motors or Chrysler or somebody, the way they purchase them. It might weigh 2 or 3 pounds, but it's only cost about $1. You're probably paying 40 cents a pound or something for the cast metal part. A forged part might be $10 or $15 for the same part, because of the forging dies and heating it up, secondary operations, finishing it, and whatnot. So it depends on the criticality of the application, but forging will essentially consolidate, remove the defects, give better grain flow. All that mechanical working means that you can later heat treat it and get even finer grain structure. In metals, finer grain size is one of the only things that gives you both strength and toughness. Okay. Most other things, you alloy it, you might get greater strength, but the toughness usually goes down. But finer grain size gives you both strength and toughness. And in order to get finer grain size, you usually have to put mechanical work in it. And often you have to put like 70 or 80 or 90% deformation into the part before you get enough mechanical work to be able to do the good heat treatment. So it's not a small amount of mechanical work that you do in these things ordinarily. To get the good structure. Now that's not true of all things. There's something called isothermal forging that was developed by Pratt & Whitney for military engines originally, and there's certain alloys that are superplastic. But let me bring that up when I get to superplasticity here in a second. That's a little bit out of sequence. Other questions? Okay. Now for forming of sheet metal and stuff, it turns out there are limitations, and I'm not going to take the time to talk about go through the details of what the limitations are to forming something. I shouldn't have brought this, but that's okay. Actually, I can pass it around since I've got it. This is a niobium cavity that was heat treated at very high temperatures, and you actually see the grains on here. This is not a cast structure. This is an annealed structure. Very high purity. If you look at it on the back side, you'll see grains that are the size of a dime, as far as that goes. That was supposed to be a superconducting cavity once. It was going to be machined after being annealed to be very, very soft. That niobium melts at around 2,500 centigrade. I wasn't supposed to bring it. It was inside one of these other things, and I didn't realize it. But it turns out, if I start out with a flat sheet of copper, and I wanted to form something that looked like this, which is not a beer can, but or a soda can or whatever, out of aluminum, but has similar shape. It turns out you can't just form it in one operation, because it turns out the stresses on the wall to do all that working to bring a flat sheet, a flat disc, and roll it all up in one operation would be too great, and you'd split the thing down here at the corners as you were forming. So it turns out you can form that in a single operation, and from that you can form that, and from that you can form that, and so there, I'm not going to pass these around, you can see them. However, I will pass these around. This is actually just a, if you remember old vacuum tube electronic appliances, this happens to be one of the cases that they, aluminum case they would put over the top of a vacuum tube in old TVs and stuff. I retrieved these from Professor Backhofen's lab. He's been retired for 25 years, but he had them before. Anyway, you had to start out with a little dish of aluminum, then there's another size, another size, another size, and they finally formed the square thing from a round disc. Okay? So we can pass those around. Okay. If I wanted to make, and this happens to be an electrical connector where you basically would put a male into a female and slide these things together for a high current electrical connector. You start off with just a simple bar of aluminum, and the first thing they do is, actually this one shows a sheared edge. They just take the bar, feed it into a machine, and the machine automatically shears one edge. You'll see this one on the back edge, they actually have already come in and formed the beginning of a process, and then they first extrude, after they form this back end, they then extrude the front end to make the tip, and then they backward extrude the back end to make the final part. So I end up with these three parts to make that part, which will later have some final machining done on it to get the final dimensions. So that's an electrical connector. Then another thing, pardon me? Yeah, this is the aluminum cans.
This crease in here, basically, then you're sliding it back out, so that crease is somewhere like up here now, or?
Yeah, the original crease, but you're doing all the forming, and it's a nice ductile metal, so it actually doesn't matter. In fact, it hardens up because of work hardening and gets stronger so far as that goes.
Okay.
But different amounts of deformation. Actually, while we're talking about that, before I go to that, let me do this, which hopefully, oh, okay, here's my magnet. This is a pot, cooking pot. Someone asked me questions about cookware. This is Millennium Cookware, has a nice aluminum bottom on the bottom. They cold bond the aluminum to the bottom, and I think that's in some of the lectures when you get to cold welding. This piece of aluminum is glued on. I need to take it off someday, but we had to make some measurements because what was happening, this is a stainless steel pot, and the stainless steel is an austenitic stainless steel, and austenitic stainless steel should be the same as, whoops, that's not austenitic stainless steel. I guess I may not have a piece of austenitic stainless steel, but some things are non-magnetic like aluminum, right? By the way, this is a neodymium iron boron magnet, so it's a fairly strong magnet. But what happened is they would make these pots, and they would finish, and these are $100, $150 pots, something. They were shipping them across the ocean, and when they got to the other side of the ocean, they had cracks in the walls, but the cracks were always at the top. And they came to me and they said, it's an MIT ILP visit, and they said, we don't know what's happening. They weren't cracked when we put them in the shipping containers. When they get across the ocean, they're cracked. And so I went to my desk and I pulled the magnet out and I said, If you go up the side here, and I'll pass this around, it's not very magnetic down here, because it is. I asked them first whether it was 304 stainless steel, which is the garden variety stainless steel. It's not very magnetic here, but up here, it's really magnetic. And what happens is stainless steel, the 302 and 304 stainless steels, the more you deform them, the more they transform. And it turns out they can do this forming operation more easily than they can this copper alloy, because the metal hardens as you work it, and so it gets stronger. Okay, you still have to do several draws to get something like this, but in any case, it's work hardened at the top. The stuff is folded in more at the top and squeezed in than it has down here, and it turns out the steel changes crystal structure, and it's called transformation induced plasticity, trip steels. And so they were going from the austenitic, non-magnetic on the bottom. Actually, yeah, if you put it on the bottom here, I mean, you're going through a little layer of Teflon, but there's almost no magnetism on the bottom because that's the original annealed sheet. It's little, okay? But here there's a little more, and it goes up the side. The more you deformed it, the more it transforms in this martensitic transformation to a ferritic type of, or martensitic type of stainless steel. And basically that type of body-centered cubic, or body-centered tetragonal in this case, stainless steel is susceptible to hydrogen cracking. In order to get the Teflon lining on the inside, they had plasma sprayed this with stainless steel powders to make a porous surface so they could impregnate the plastic. I may, in fact, on the tapes that do adhesive bonding, I may have explained some of this on that one. But in any case, they had plasma sprayed it. In the plasma spraying operation, they had introduced some hydrogen. Hydrogen's called delayed cracking. No cracks, ship it. On the way across the ocean, it has time for the hydrogen cracks to show up where you have the maximum amount of the magnetic crystal structure of the steel. You also have residual stresses up here. You have to have stresses to get the hydrogen cracking. So that's the story of residual stresses, transformation, hydrogen cracking, all coming together to give you a defect in your product. And the solution to it, well, there's a number of solutions. You could change the type of steel, but then you have more difficulty in forming, okay, because some steels form more easily than others. That one forms very readily. Or after you do the plasma spraying of the powders, you can heat it in an oven at about 350 degrees for 4 or 5 hours to drive all the hydrogen off, so the hydrogen is not there to do the damage. Those are probably the two most practical ways. Either change the steel to one that won't transform and be susceptible to hydrogen cracking, or get rid of the hydrogen. Okay, so let's get these out of the way so I know what I'm talking about. Next one I was going to show you, I sent around those little copper connectors. This actually is another fairly simple part that, yep.
Does it have to be atomic hydrogen? I mean, this hydrogen in the air, will that...
Hydrogen in the air is diatomic and will not diffuse into steel unless it's at high temperatures. High temperatures being like above 1,000 degrees Fahrenheit. You can diffuse hydrogen in steel, but at room temperature, the diatomic hydrogen is prevented from getting into the steel by the iron oxide that's on the surface. At higher temperatures, the hydrogen can react with the steel, become atomic hydrogen, and diffuse in. Now, in welding, you have plenty of heat from the heat of the arc, and it creates monatomic hydrogen in the arc, and so there's plenty of hydrogen that can get in. In electroplating, you have hydrogen ions, and so in electroplating, you end up with hydrogen ions in solution, which are monatomic hydrogen, and they'll diffuse right into the material. So electroplated bolts that have an electrogalvanized or a cadmium electroplate, high-strength bolts, they put the zinc or the cadmium on there to keep them from getting corroded. But there are requirements that those things have to go into a bake-out furnace at 375 degrees Fahrenheit within 1 hour of the electroplating operation. Okay? I know a helicopter part that they were doing some nitrided, and then chemical cleaning. And the chemical cleaning, just the acid cleaning, you're not passing current through it, but they're hydrogen ions in an acid solution, right? That's what acidity is the hydrogen ion concentration. And you can introduce hydrogen. So they had this high-strength steel part that was the drive shaft, basically, for the engine. And they would heat treat the part and do part of the cleaning operation, and then they would send the sample off to the lab to check that the heat treatment had done what they had wanted. And then 2 or 3 days later, they would put it in the process for driving the hydrogen off, which means that the cracks had already formed. Typically, hydrogen cracks form within 1 to 4 days. In a nuclear submarine, the Navy has a spec that you shall not do your non-destructive testing for cracks for at least a week after you make your weld, because you want the hydrogen to have done its damage before you look for the cracks. If you look for the cracks within the first hour, you'll find nothing there, just like the people who shipped the part, the pot. Okay, no cracks when they shipped it. A few days later, cracks show up. Those cracks actually kept growing for a while in my laboratory just because of residual stresses and other things. The structural welding code for steel says for the highest strength steels, these are 100 KSI structural steels, which are not very common, but it says you're not allowed to do the destructive testing, radiography and other things, looking for cracks and other flaws within 48 hours, if I remember. You don't have to wait 2 days rather than 7 days. The Navy's more conservative on nuclear submarines. Okay, any other questions? Yep.
Can you refresh my memory what the difference is between austenitic and martensitic?
Okay. Martensitic steel, or austenitic, is the stable crystal structures of iron in high temperatures. If you look at the iron-carbon phase diagram, we got a paratectic up here, which we don't have to worry too much about. But so this is temperature, and this is percent carbon, and this is not exactly the scale, but nonetheless, that's the iron-carbon phase diagram. I got liquid, I've got delta iron here. This is delta plus liquid. This is gamma iron, which is face-centered cubic. This is alpha iron. There is no beta iron. Anybody know what happened to beta iron? Beta iron was the magnetic transformation above the Curie temperature. When people originally were studying steels 100 years ago, they would actually do calorimetry, and they'd see how much the temperature, the heat the steel absorbed and gave off as you heated it or cooled it. And there turns out there is a transformation from going ferromagnetic to paramagnetic, and it's in between here. And so they saw a temperature change in the steel, but it wasn't a crystal structure change. And anyway, since they saw it on their little heat diagram, they call it alpha, beta, gamma, and delta iron. Well, when they actually started doing X-rays in the 1920s and learned about body-centered cubic iron at low temperatures and face-centered cubic, they couldn't find a different crystal structure for beta iron, because there isn't a different crystal structure. It's what we call second-order phase transformation rather than first order. A crystal structure change is first order, a magnetic transformation is second order, and so beta iron, we don't talk about beta iron anymore. But all through the 1920s and 30s, there were people debating, metallurgists debating whether beta iron existed or not. In any case, to answer your question, this temperature is 723 degrees centigrade. This is 910. This is 15, call it 1510 centigrade up here, the melting point of pure iron. The cast irons are over here. And we can get down to around 1200 some centigrade or so over here at the lowest melting temperature of the cast irons. So cast irons melt at lower temperatures. They have a lot of carbon in them. That's one of the things that makes them more brittle, is the high carbon. A lot is, this is 2.1%. You haven't memorized the iron carbon phase there? Or no? You're not a metallurgist, right? This is not the scale, because this is 0.8%. Okay, the eutectoid temperature right here. In any case, if I put a lot of nickel in steel, which is face-centered cubic, I will stabilize the gamma crystal structure all the way down to room temperature. And that's austenitic stainless steel. okay? Gamma is austenite, named after Robert Austin, a British metallurgist of 100 and some years ago. Alpha iron is known as ferrite, and it's body-centered cubic, and it's also magnetic. It turns out the face-centered cubic crystal structure of iron has the right number of electron orbital, or has the proper electron orbitals to be ferromagnetic. The face-centered cubic crystal structure is not ferromagnetic, it's paramagnetic, even down at room temperature. So there is a Curie temperature of pure iron above which you lose your ferromagnetism, and it actually is right in here somewhere. Can't remember the Curie temperature, but the Curie point, and the Curie point drops like this. But if you can stabilize by adding nickel or manganese, high amounts of manganese, this would be like 10% nickel and 6 or 7% manganese, you can stabilize the austenite crystal structure, and the steel will be non-magnetic even down at room temperature. If you take it up here and quench it down, you're going to form a very hard, almost body-centered cubic crystal structure. It's actually body-centered tetragonal. In the iron carbon system, the carbons will take a perforder orientation, and they will actually stretch the body-centered cubic structure so it has a little bit longer axis in the vertical direction as opposed to the two side directions. And so that's martensite, and martensite is metastable. If you heated martensite at 1,000 degrees Fahrenheit, but what's that, 600 something, 650 centigrade, heated martensite up here for a long period of time, it would all decompose back down to alpha iron, okay, because martensite's metastable. The structure that's in that pot that's going around starts out, is supposed to be austenite as an iron chrome nickel alloy. It transforms not with temperature but with mechanical deformation to the body-centered tetragonal martensite, which makes it ferromagnetic, which is why you can feel the difference. And if you heat treated it for a long time, it eventually would, annealed it at a lower temperature for a long time, it eventually would transform to fully ferritic iron. Does that answer your, probably more than you ever wanted? But in fact, it gave me a chance to tell you where cast irons are and steels are. Steels are all, the practical steels are all kind of over here. There are very few alloys that are between 1% and 2% carbon. There are a few tool steels, but most of them are either cast irons where you're going for low melting, ease of casting, or steels where you're going for all kinds of fancy properties by changing the carbon content and all the other alloy content. But the iron carbon phase diagram is probably the most important phase diagram commercially in the world, because it controls a $400 billion a year business worldwide. Okay, other questions? Now, this actually is another forming operation, and the part that's going to be made is just this little insert part that if you ever buy cheap wood furniture at Walmart or Target or something, or even plastic furniture, and it has metal screws to hold it together. And this would be like a computer desk or some bookcase or something. Because they're using chipboard before, underneath the plastic laminate, the fake wood finish. If you try to put threads in that, it would just strip the threads in the chipboard, because chipboard is just sawdust and glue, right? So they basically put an insert in there which has threads in it. So now I can actually tighten a metal screw down with a threaded connector. And this is knurled on the outside because basically they just drill a straight hole. In fact, sometimes they make you do the insertion of these things when you're assembling one of these things, right? And you hammer it in and whatnot. Well, how do you make one of these? Well, you start out with a rod of steel, in this case 3/8 inch diameter steel. You just shear it off. And so the first one here is the sheared end. The second one is the first formed end, and all they did was size it. They just squared it up and they made a little dimple on this side, because the next one is sort of like those copper parts. You're going to do a backward extrusion and make a hole in it. Then you're going to make the hole deeper because you can't do the forming operation in just one step. Then you're going to put a flange on the end. Then you're going to punch out the center, and down inside here, I've lost it a couple of times, so I got a piece of Scotch tape over it. But this is the only piece of waste. It's a little, if you want, you can, I'll take it off. Just try not to lose it. It's this little, it's a little, this is the only scrap from making that part, okay? And then the next operation, oh, this is just the part after they punched out the thing, so that, these two go together. This one they put the knurling on, this one they do the threading operation on the inside, and then they electroplate it to keep it from corroding. So there's all the parts. That's done in a, what do we call this process? Got a mental blank here. It's basically an impact extrusion type of machine, and it just goes pound, pound, pound. But we call it, can't remember what the generic name is for this type of thing. But some critical parts, like forged parts on cars, like some steering knuckle components that need a little better quality. Oh, it's a heading operation. It's cold heading. That's called cold heading. Okay, because they do it cold. There's also warm heading where they heat up the bars a little bit, and essentially you're hot forging. But it's basically a cold forging process. And you go through all those steps to make a simple little, 5-cent part. But the machine is just pounding away. Now, I think in the adhesives lecture, I actually may have brought those in. You may see that on the tape. Because in order to do that, they had to develop a surface on that original part, and you can't feel that original sheared part anymore, but for about the first 10 years, if you pick it up, it feels soapy. And the reason it felt soapy is because after World War II, they learned if they phosphate the surface of the steel, they can make the surface, the iron phosphate gives a very rough surface, and then if they put zinc stearate soap on there as the lubricant, then the porous iron phosphate surface holds the soap and allows you to do a lot of deformation and get good lubrication. People tried cold heading in the 1930s, and they just wear out their dies because they didn't have a lubricant that would spread across the surface. They didn't have good bonding of their lubricant to the surface. Just like in that cooking pot, in order to get the Teflon on the surface, they had to have a porous surface to melt the Teflon into the pores in order to get good bonding. When you get to the adhesive bonding lecture, I'll talk about why it's hard to bond plastics because they have low surface energies. So you have to get a good mechanical bond. Well, in that cold heading operation, they had to develop an iron phosphating on the surface to get a bond between the glue, the soap that acts as the lubricant. It's been handled so much now that we've all washed our hands with the soap that's on there, and the soap is gone. We need a new bar of soap. Okay, someday maybe I'll rephosphate it and soap it up again or something. But that was one of the things that made cold heading possible. Now, if you want to make more complex parts, or not necessarily more complex, but if you want to make parts out of a piece of sheet metal and stamp little parts, or you want to make beer cans, 40% of all the aluminum in the world goes into making soda cans and beer cans. Okay? It turns out this particular operation is to make a bunch of sheets that stack together to make a heat exchanger. So we've got plated steel parts. In this case, this one was copper plated, and they have some little turbulators on here because you're going to flow a liquid through this side and then maybe air on the other side, or maybe another liquid on the other side. But in order to make those simple little sheets that are going to stack together to make a heat exchanger, you basically have to go through what's called a progressive die. In a progressive die, you feed in the sheet metal, and you have to first cut the edges and then form each individual part until you finally get to the part that you want to stack together back here. So the whole thing, this has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 steps to the progressive die. This progressive die to form this material is probably $200,000 to $300,000 for the die, for the parts that go through the stamping machine. This just happens to be another one. I'll probably pass. No, I can pass both of them around. Pass all three of them around. So you can see the final product. So and the reason is if you try, and shaping those dies is more art than science, even today, although with fancier computers we are getting to the point where we can calculate the stresses on each shape and try not to overform it, because it, just like these parts, you'll break at the corners if you try to do too much forming in one operation. However, about 35 years ago, Professor Backhoffen and his students rediscovered something that someone had discovered and published in the literature in the 1930s, 70 years ago, called superplasticity. And it turns out if you take sheet and you get finer and finer and finer grain size, typical grain size in a metal, well, I passed around some stuff that has grains that are a centimeter in diameter. That's very coarse. You don't usually see that. You saw it, but you saw that in the niobium piece I sent around. You saw that in the copper piece that continuous cast piece I passed around the other day. So you can get grains that are a centimeter in diameter by normal solidification processes. If you want to get larger grains, you usually have to do it in a special gradient type of furnace, and then you can grow single crystal turbine blades. And of course, the largest commercial single crystals that we use in the world are what? Doug, speak up. No.
Oh, Chris, silicon.
Silicon. 12-inch diameter silicon, right?
I've seen 16-inch.
So you've seen 16?
We have a 16-inch
Piece.
wafer.
Right. And these things are growing about 10 feet tall, 15 feet tall. I mean, eventually they're going to slice them into wafers, but that's a good-sized single crystal. And there's a lot of value in a product like that. Now, there are turbine blades. I've seen single crystal turbine blades that weigh about 100 pounds, but that's nothing compared to the silicon boule, okay? But, and those turbine blades are worth quite a bit. Those are for land-based turbines, generating electricity and stuff. In any case, so you can get, but the typical grain size, if I were to analyze the grain size in a piece of copper like that, I might find something on the order of 5 to 50 microns, okay? 50 microns being 20 thousandths of an inch. 5 microns being about 1/5 of a mil, right? Or 0.0002 inches in diameter. If you get down another order of magnitude in grain size, down to about 1 micron or less, it turns out the material will start to creep at various temperatures. And remember, creep is how if you put the silly putty on the table over time, it'll just flow. Well, it turns out you get down to fine enough grain size, the material likes to flow along the grain boundaries, and now you have a very substantial fraction of your total crystal structure as grain boundary. And this happens to be an aluminum zinc alloy, and this will creep at room temperature. So instead of coming in with a forging press where you just wham, within a fraction of a second, if you try to form this in one operation, it flows like glass. It flows like we call it Newtonian fluid. A Newtonian fluid doesn't neck down and stretch and break in one spot. It flows uniformly. No matter what its cross-sectional area is, its proportional reduction in area, even though the area is different at different spots. That's why glass blowers can take glass and stretch it out into great big long things, and you get super plasticity at high temperature. Now, glass doesn't have any grain boundaries, but metals will start to behave like glass in terms of forming, and this aluminum zinc alloy will do it at room temperature. Now, this probably ought to go to the Smithsonian. This is the last one I have, but they actually got some dies, which were the final forming dies from some of the silversmiths down here. This was for some silver candy dish, okay? And Professor Backhoffen students in the 1960s, when they rediscovered superplasticity, borrowed dies from some of the final finishing dies from some of the silver companies, some things they weren't using, and they would do the forming operation all in one operation rather than a whole bunch of steps. They could make a single draw in the superplastic material. IBM in the 1970s, when they were still making typewriters and little office machines and they had all kinds of zinc-based parts, had a huge program. This is when IBM was very, very profitable. Had a huge program to make zinc parts rather than die-cast parts for all their office machines. And they could form it at room temperature and get very good precision to form the parts, but they couldn't solve the problem of getting the grain size large enough that it wouldn't continue to creep at room temperature, just like the silly putty. So they'd actually put the parts in the office machine, and then over the next 6 months, all these precision parts would just kind of sag, you know. And apparently the manager of this program was just a real jerk, and everybody hated him. They canned the program, including the manager, and so all these people got laid off. But as a final parting gift, they made an ashtray out of this super plastic material to give to him, and they put a rubber band around it just so it would have enough stress so it would keep creeping, to help remind him how they all lost their jobs because he couldn't solve the problem. In any case, to form something like a beer can, you got to go through all these types of operations, but you actually do something, it's called drawing and ironing. You actually stretch the material out, and you can make a fairly long thing. Now, beer cans, this one's fairly thick. I'm not going to pass it around. It's an old one I have. But they're getting down to like 4 or 5 thousandths of an inch thick. Okay? Why? Because the cost is in the material. Okay? If you can get more aluminum out of there. But the problem is, beer cans are not as bad as soda cans. Soda cans, you got a fair amount of CO2 pressure. You might have something like close to 100 psi, I think. As the pressure, and so they use supercomputers to do the calculation on the stresses because it's 40% of the aluminum business. Okay, if you didn't have part of the can market, you wouldn't be able to make any money in the aluminum business. You can't ignore 40% of the market. Anybody have any questions on that? Let me talk now about isothermal forging. To make this, you hand me the forging. For certain nickel-based alloys that are used in jet turbines, it turns out you can get very, very fine grain size, so they become super plastic. Not at room temperature, but at high temperatures. And so Pratt & Whitney in West Palm Beach, the military division, 15 or 20 years ago, developed isothermal forging of IN 100 nickel-based superalloy, where they could get very fine grain size, and they would come in with these graphite or diamond, or not graphite or diamond, but graphite dies that would take high temperatures for a long period of time, and they just slowly squeeze the final part. Okay, and they get something that was a more complete final part than this one. This one's going to have a fair amount of machining. And the reason for that is because of what they call the buy-to-fly ratio. The Air Force is very concerned about the buy-to-fly ratio. Anybody know what it is? It's a very simple ratio. If I'm making a part for an aircraft, back in the early 1980s, I might have to purchase 100 pounds of a superalloy or a titanium alloy for every pound I was going to fly as the final part, which means I'd have to forge it and machine away 90 to 99% of what I had. I think the average for all aircraft parts for the Air Force was something, a buy-to-fly ratio of something like 30 to 1. There were some parts that were very complex and had very thin sections. They needed the quality of the forging, but they didn't want the weight, because you can't make the forgings too thin, or the thing is it's not going to be able to take the operation, or you'd have to go through too many dies, or it'll oxidize on the surface at the high forging temperatures. But the buy-to-fly ratio was something like 30 to 1 as an average. That means you're throwing away 29 pounds, actually not throwing it away, it becomes scrap. So you take something, if you're talking a nickel-based superalloy, you're taking something that's worth $15 to $30 a pound, and I'm going to make a part, and let's say it's a 100-pound part. I gotta produce 2,900 pounds of scrap to make that 100-pound part for a turbine disc. And if that material is costing me $20 a pound, 2,900 pounds times $20, and you're talking very expensive parts. That's why turbine discs cost $50,000 because now you may get some of the value back. The scrap may be worth $10 a pound. However, the machining cost, because I got to machine that, I'm machining 29 pounds of chips to make every pound that I'm going to fly. So a big program in the 1980s and into the 1990s was near net shape. And near net shape went back everywhere. It was a huge program to look at the whole metal forming operation. Near net shape manufacturing, they went back to the casting operation. Could they cast things closer to net shape? And the dog bone structure at Chaparral Steel was not an Air Force program, but it was the same idea. If you're going to make an I-beam, you cast it in a dog bone shape rather than a rectangle. And Chaparral went from 29 rolling steps to about 10 rolling steps. They cut out 67% of their passes through the rolling mill to make an I-beam in the rolling operation by going to a closer to near net shape casting. Okay, then they went to things like isothermal forging. The isothermal forging developed by Pratt & Whitney was a near net shape, so you had to do less machining of the part to get the final part you wanted. And a few years ago, I think the ratio was down to 10 to 1, and I think their goal is somewhere in the order of 5 to 1 now. Well, that still means 4 pounds for every pound you fly. There's 4 pounds of scrap, and you lose about half the value of that scrap, because as it comes back to the metal mill as chips, yeah, it's valuable, but it has to be remelted and recast and everything else, right? So the buy to fly ratio and near net shape manufacturing is still a huge problem. And that's one of the reasons why people got so excited about 10 or 12 years ago with solid freeform fabrication. Or SFF. And that's the one I passed around, the little ceramic part where people would lay down a layer of material at a time. Originally they were doing plastic parts, and they would come in with a laser beam and they would cure the plastic in place. So you had a liquid polymer solution, and you have the laser beam come in that was transparent to the polymer was transparent to the laser beam, and actually you'd have two interacting beams, and when they had enough power at where they interacted, they would polymerize the polymer, and they would essentially cast the polymer using laser energy as the energy source, and they do it pixel by pixel, if you will, in 3 dimensions to build up a part. The original machines were like 100,000, then they got to, they're about $1 million a piece now. And the plastic parts, there's only certain types of plastics. It was really just for prototyping, to see if parts would fit together. So you could basically take some object that you had as a CAD file in a computer, and you could send the file, quite a bit of work on the software, over to the solid freeform part maker, and a designer could change the design on a part, and a day later have a part back. And it only cost about $2,000 for that little part made out of plastic, which if you blew on it a little bit hard, it would shatter. But nonetheless, okay, it wasn't a commercial part. But then people started thinking of all kinds of ways. MIT invented what's called 3D printing. Professor Sachs in mechanical engineering, Professor Seema, kind of just started using inkjet print head and would squirt out a slurry, and that little Taj Mahal plastic thing that I passed around the other day was an example of 3D printing of a ceramic part. The first applications of that were not to make the actual part, but to make biomedical parts, hip implants for people, so that you could design a hip implant personalized for the patient. So the physician could go in there and put in the dimensions of the implant, metal implant he wanted to put in the patient, and ship it off to a casting shop, and they would basically make a ceramic mold of that shape by solid freeform fabrication, make the ceramic mold, essentially a lost wax type of casting operation without the wax. Okay, so you make a mold, you pour it in, you have a customized casting just for that patient. Well, you can afford that when you're talking hip implant surgery, which is $30,000, and so you pay $5,000 for the implant rather than $3,000. You know, it's not a big deal. However, the last I heard, the really big application of 3D printing was for drug delivery, in the sense of one of the problems they have when they, you take some pills and they have the actual 99% of that pill is inert ingredient, okay? The actual pharmaceutical product that's in that pill is 1% or less of the total. And typically, they mix these things in not huge batches, but they need to have uniformity, because you don't want to have twice the drug content in one pill and only half in another. They want uniformity. So what they found is they could just make placebo type of pills, and they could use inkjet printing to squirt the drug into each individual pill and have a controlled amount. So they basically took the whole idea of solid freeform. Why? Because there's a lot more money in the drug business. I mean, the Colombians have known this for years, right? And the people in Afghanistan, there's a lot of money in drugs, right? But even legitimate drugs, there's a lot of money in drugs. And so what drove the research in these things? It kind of went first from the idea of making parts for manufacturing, and then they said that's too expensive for real manufacturing, although the people who do this will still tell you it's cheap enough for real manufacturing. But I don't know of any automobile part or even any aircraft part that's being made by solid freeform fabrication. They might make the molds and might make the prototypes. Then they got into the medical field, because now you get to even higher value added per part or per pound, because it's now quality of life type of price, not value of pound, weight saved and fuel costs. And then they went to pharmaceuticals. So they kept on moving up the chain in how to use this technology. But it's still, the Defense Department is still very interested in it. They would like to be able to make one-of-a-kind parts in the computer. Okay, we'll see you tomorrow. Thanks.